Okay, so hi everyone, it's Tam. So today you will have a guest lecture on hallucination, given by, I'm okay, so I suppose you would already know me. Um, I will get straight to the content. So what is hallucination? Um, this is when system generates garbage content. In the case of large language model, it would be when the model generates conflicting content within the answer itself or to the question, or when the answer content cannot be verified with existing sources. In the case of machine translation, it's a bit more simple because we just have to look into whether the output translation is relevant to the source sentence. So it's easier to ground whether the case is hallucination or not in machine translation, in my opinion. So today we will spend most of our time focusing on hallucination for large language model. But then we will also skim through the case of hallucination in machine translation at the end of the lecture. So hallucination in LLMs. We will first talk about the taxonomy of hallucination. So in some survey paper, they divide the cases of hallucination into two main subcategories. The first one is factuality hallucination. It happens when there is a difference between the generated content and verifiable real-world facts, as in we can actually find the facts that disagree with the output from the LLMs. And for this, there is two subcategory: factual inconsistency and factual publication, which we will look at some example later. The second main category for hallucination is faithfulness hallucination. And this is divergence of the generated contents from user instruction context provided by the input, or self-consistency within the generated content. Again, we will look into that right now. So the first type of hallucination is factual inconsistency. So here we have an example where the input is telling me about the first person to land on the moon, and the model output is some name that is completely wrong compared to the fact that we already know, that we can verify given the existing resources. We're supposed to be Neil Armstrong. So this would be factual inconsistency. The next type is factual fabrication. So here is tell me about the history of historical origins of unicorn, and then the model output was some seemingly confident information about the history of unicorns. But as you know, we cannot verify whether this is true or not. We have no information about unicorns or their history. So this would be like a different type of hallucination as before, because now it's just fabrication. We cannot, it's just not verifiable with the real world facts, but we can also not say that for sure that this is wrong. The next type of hallucination now into the faithfulness category is instruction inconsistency. It is when the model doesn't follow the instruction given by the input. So here the example is we have the user input translate the following English question into Spanish. What is the capital of France? And then the model output is the capital of France is Paris. So instead of translating the sentence as we want, the model just answer the question which diverges from the instruction. So this would be instruction inconsistency. The next type, also fall into the faithfulness hallucination category, is context inconsistency. So, so in this case, the user input is this long, and then we would focus on this part originating in the Great Lakes region of Central Africa. And then, well, the task is to summarize this paragraph. And then the model output is like this, where they have this conflicting information that the mountain ranges of Central Africa. So, so you can see that there is some inconsistency between the model output and the context of the user input. So this would be context inconsistency, which is different from the ones before, because here the model did adhere to the instruction of the user, which is to summarize the paragraph, but still the context here is just wrong. And yes, last one, also falling to the faithfulness category is logical inconsistency. So here the example is that the user input would be solve the equation 2x plus 3 equals 11 step by step, and this is the model output. So logical inconsistency is when the model is inconsistent within its own output, because here it said that divide both sides to get x equal to 3, which is wrong, because if you divide both sides of 2x equal 8, you would get x equal to 4. So yes, it would be some inconsistency within the output of the model itself. Okay, so that's on the taxonomy of the hallucination. Now we would go into the process of hallucination. So the first cause of hallucination would be from the training data itself. And the first thing is that in the training data, there can be misinformation and biases. And the first thing we will look into is imitative falsehood. This is where training data contains wrong factual information. So there was an example where the input is who is credited with the invention of the light bulb, and then the LM output is Thomas Edison invented the light bulb. So as you can see, this is actually a false information which was believed in quite a long time for so because of the human misbelief in this wrong information, this also affects the training data that we gathered from, for example, the internet to train these models. So it, as a result, leads to the fact that LLMs also output this wrong information. That is the first type, and this one would be quite difficult to solve, but we will look into that later. The second type is duplication bias. So this would be about the training data contain duplicated information. And this would be harmful to the LLMs in the sense that when the LLM sees so many repeated content, it would tend to memorize them, and then would fall into just output whatever is memorized rather than actually understand the content and generate context. So for example, here we have the input, please list some red fruits excluding apple. And this is the output by LLMs. Red fruits are red apples, watermelon, cherries, and strawberries. So in the paper, they said that in this example of this LLM, the phrase red apples, watermelon, cherries, and strawberries are repeated a lot in the pre-training data, which leads to the LLM now just output the whole thing, even though in the input, they explicitly asked for not including apples. So this would be one type of source for hallucination. The next one, also hallucination from data, is misinformation and biases on social bias. So this would be the biases that related to, well, social factors like gender or nationality in the training data. So here we have an example. Provide a summary of the following news. Dr. Kim recently published a something paper on quantum computing. And then in the output of generated by the large language model, it said that Dr. Kim from South Korea recently published a paper. So the thing here is that in the original input, there's nothing about the nationality of the person. But here, the large language model just output from South Korea because of the biases that name Kim is probably from South Korea. So this would be one type of social bias. Also, hallucination from data is a knowledge boundary. So most of the time, large language models are trained on, well, general knowledge data because the data is mostly scraped from the internet. So when it comes to specific domain, we can have a domain knowledge deficiency because usually the training data on so small and niche domain would not always be publicly available to train LLMs on. Another type is outdated factual knowledge. Because once we have changed the LLM, we cannot change the internal knowledge, like the set of weight that we use for this LLM is now fixed. So if we don't do any external action to update it, then the information stored in the LLM is going to be fixed. And then it would lead to the LLM hallucinate and output outdated knowledge because it simply doesn't know about the updated ones. And the next one is knowledge shortcut, where the LLMs resort to shortcut rather than genuinely understanding the knowledge. So the shortcuts here could be positionally close, as in some tokens happen to be close all the time in the training data, close to each other, or co-occurrence statistic. So one example would be when we ask the large language model, what is the capital of Canada? And then the output would be Toronto is the capital of Canada, because in the training data, whenever Canada is mentioned, then it's most likely that Toronto is also mentioned. So this is like the case of co-occurrence, and then the model just kind of resorts to this shortcut rather than actually understand that the question is asking for the capital and not about the specific city. Another type of hallucination from data is knowledge recall failures. And the first one is long tail knowledge, which are knowledge that is very rare in the training data. So an example would be where we ask, please generate a biography for this person, George James Rankin. So this name is a politician that appears in the wiki training data for the large language model. So it just happened once and it's really rare. So this is in the training data, but then when we ask the model to generate the biography, it just wrongly output that this is a dedicated educator, which is wrong because it should be a politician, but because of this knowledge is so rarely occurred, it's difficult for the large language model to actually learn. The next one is complex scenario, is where maybe, for example, we ask large language model to answer some question that requires multiple hops of reasoning. Then the LLMs might not be able to have such strong reasoning capability. So for example, we have the input, if Mount Everest were to descend by 500 meters, which mountain would be the world's highest peak? And in the output, it still outputs that Mount Everest will still remain the world's highest peak, even though in the training data, it has the information about another highest peak, another peak, which would have become higher if Mount Everest decreased by 500, but it just failed to reasoning and fetch the other information. So in this case, it might be too complex for the large language model. So that leads to hallucination. So that is all for hallucination from data. Any question? Okay, so another source of hallucination now would be from training. And the first source would be architecture flaw. So hallucination can come from the inadequate and directional representation. So as you know, large language model is also just a transformer, decoder only. And during generation, we do autoregressive decoding, as in we generate the sequence from left to right, and we keep getting the prefix output as the input and then generate the next token by token. And the thing here is that because the sequences is generated from left to right, there is no chance for the model to actually correct what it has already output. And then if it outputs something bad in the beginning, it's most likely just leads to, I don't know if you can say this, but it's going to be some sort of cascaded error. And then the whole answer is just going to be worse and worse. Another architectural flaw is this attention glitches, because there is some limitation to soft attention. That is when the input sequence is really long. The attention score will become diluted across positions of the sequence. So it's going to be difficult for the model to focus on which part is important when the sequence length is too long. Another source for hallucination from training is exposure bias, which I believe you might have heard about, is that when we train large language model, we will train with force decoding, as in every training step, we fit into the model the gold standard output prefix in order for the model to predict the next token. However, in reality, during inference, we don't have this gold standard prefix. We have to input to the model, whichever have been generated by itself in the beginning. So there will be some mismatch between inference time and training time, and this would be called exposure bias and would most likely lead to erroneous output and, in severe cases, hallucination. And the next one would be hallucination from alignment, where the first one is capability misalignment. This is between the fine-tuning phase and pre-training phase. So it can happen that during pre-training phase, the model is pre-trained with some general knowledge, but then during fine-tuning, it gets to fine-tune on some specific domain. So somehow we are teaching the model to output some content that is beyond their own knowledge boundaries by this fine-tuning step. So as a result, during inference, the model would learn this pattern and then just try to output things that is out of its knowledge. Another type of misalignment is belief misalignment. This, instead of happening in the fine-tuning phase, it happens during the human feedback phase, because in this phase, we try to make the large language model output whichever that fits the preference of the human. So it would be trained to produce output that diverges from their internal beliefs, just for the human preferences. And this could cause hallucination as well, because it would kind of neglect what is true and just try to output whatever the human wants. And those are the causes from training. Another main source of hallucination is what happens during inference time, where we have the first cause is from sampling randomness. So when we use large language model, sometimes we just want the model to have more diverged output. And usually people would introduce this by increase the sampling temperature, but by doing this, the low frequency tokens is more likely to be chosen, and then it would increase the risk of hallucination. But of course, here, if you're looking at it from different perspective, you will think that you might see that this would depend on the use case, because having more diversity would be useful when you want the large language model to create some, I don't know, entertainment content, like some stories, for example, and in that case, maybe more sampling temperature would make sense. But if you wanted to create something correct, then it might not be good to set the sampling temperature to be too high to avoid hallucination. Another source, also during the inference phase, is imperfect decoding representation. And the first one is insufficient context attention. So some paper doing explainability and looking into the attention score, and they see that when the large language model output, the next token is supposed to look into the source sentence and also whatever that have been generated so far. But they have found that most likely the large language model tends to give priority to the nearby words, as in if it keeps generating a long sentence, it's most likely it's going to focus on its own previously output tokens rather than the ones during the source provided during the source sentence. Another source of hallucination is softmax bottlenecks. So the softmax layer produced the distribution over the token vocabulary by doing the dot products between one single hidden state of the token and the embedding of the words in the vocabulary. And some papers have found that in this way, no matter how large the large language model is and how much training data we use, it's not possible to generate all possible distribution using only one single hidden state. So, so the softmax layer might not be as generative as we wish it could be. So this can also be one possible hallucination. So that is all on the process of hallucination. Now we will come to the part of hallucination detection. So one obvious way is that we can just retrieve the external facts that we have known and then compare it against the output by the large language model, which people call in literature fact checking. Some people have proposed a pipeline to do this fact checking process where they first decompose the claim made by the large language model, and then they retrieve the raw documents and then retrieve the document in the fine-grained manners, as in where exactly this fact happened, and then summarize the retrieved document according to the claim, and then classify whether the claim is correct or not. And as you can see, it can be quite energy consuming process, because we have to go through so many steps, and we also have to decide where are the sources of documents that we're going to retrieve. So I would say that this is not always easy to do. So people have been also looking into uncertainty estimation, as in looking into the large language model itself on how confident it is on its output. So in this way, we would not be too reliant on the outside world facts in order to check the output of the large language model. And for this, there are several ways. We can look into the large language model internal states in order to decide whether one output is confidence by the model or not. And here we can look at the token probability, which is generated during inference, or the entropy of this distribution. And intuitively, the higher the probability, the more confidence the model is on the output, and the lower the entropy, the better. But however, we should also consider that because of exposure bias, most of the time, not just large language model, but any neural network would be likely to be overconfident on its output. So this should only be like a pointer to the quality of the output. Another way is to do self-evaluation, where we ask the large language model to reconstruct some original concept from its generated explanation, as in we just give as input to the large language model some concept and then ask it to generate some explanation and see whether it can reconstruct. And all of this can be done by prompting, so it might be a bit easier to implement. But as you can see, it would be also quite time consuming, because then we need to ask the large language model to do a lot of inferences. Another way is to do hallucination attacks, as in we try to do something to the input of the large language model to try to probe and try to make it output hallucination. And one paper have proposed to use gradient-based token replacement, as in just replacing the tokens in the input, and try to see if it would make the model output hallucinations more often. And those are the approaches on detecting hallucination in using the LLM internal states. Another way of looking into it is to investigate the LLM's behavior without looking into the model itself. So these approaches would work for some black box API only LLMs like ChatGPT, for example. So one way of doing it is to sample multiple responses from the LLM for the same prompt. So we can do this by setting the temperature, or just repeat the prompt with different seed. And then we try to evaluate the consistency between the output from the LLMs And of course, intuitively, if the model managed to generate similar contents across different runs, then it's more likely that the model is confident on the output. Another way is to incorporate additional LLMs. So here we can use some other LLMs, maybe stronger ones, and use it as examiner to question an examinee LM, as in we would use this external LM to probe the large language model of consideration for question, and then we would again collect the output by the examinee LMs and check for the consistency. And also again, the more consistent, the more likely that the output is with high confidence. So there are several hallucination detection benchmark, and there is some public leaderboards on Hugging Face, which you can look into. So here I only mentioned one example of these hallucination detection benchmark, which is called HalluEval. So this benchmark is a collection of generated and human annotated hallucinated samples. So there's two ways of using this benchmark. The first one is that we can input these hallucinated samples into some large language model and then see whether this large language model can actually tell that this is hallucination or not, which is also a pointer to whether the LLM is prone to hallucination itself. Or we can pair the sample in the data set with human evaluation, as in performing human evaluation ourselves, to test whether an LLM is hallucinating or not. So, yes. So that is all on the detection and the causes of hallucination. Any question so far? Okay, then we'll move on to hallucination mitigation. The first one is how do we mitigate when hallucination comes from data-related sources. So as we mentioned before, that there can be many things that goes wrong in the pre-training data of the large language model. So the first way of handling it is just to do manual curation of the pre-training data set, as in we would use human resource to look at the training data and see whether there is low quality or wrong facts in the training data. However, this is quite problematic because the definition of foundation models is that we will try to pre-train it on a very large amount of data. So given this large amount of data, it could be quite problematic if we just try to look at everything manually and try to filter the data ourselves. And another way to clean up the data is where we look at de-biasing. So as I mentioned before, it can be problematic when the training data contains so many duplicated content, which makes the model just memorize everything and output things without thinking. So here we can do deduplication of the training data. And for this, we can do it on the surface level, as in we try to see how like we will look into exact word matching to see if an exact text segment is repeated throughout the training data, and then we deduplicate it. But also we can look into the semantic level where we just embed everything with some neural model and then deduplicate the ones with very high similarity. But of course, this is also quite resource consuming because then we have to embed everything and then look over everything pairwise. So it's not that much of a straightforward task to do. And to avoid societal biases, we can do carefully selecting diverse, balanced, and representative training data. Now it sounds a bit more feasible to do. But the thing is that we can only do this when we already know what kind of bias can happen in the training data. So for example, we already know that gender bias can happen a lot when we train large language model. Then we can look into the training data and try to balance the data between men and women but still there can be some hidden biases which is not that obvious during training time and which would only show during usage of the large language model. So for those cases, it would still be quite difficult, and we just have to learn as we go what kind of biases and how are we going to choose our training data selectively and in a smart manner. The next one is we would try to mitigate hallucination that is sourced from knowledge boundary. And for this, we would look into knowledge editing because, as I said before, once the large language model is trained, we would result in a fixed set of weights. And the thing is that how are we going to change and update it for more updated knowledge or more correct knowledge? And one way is to directly modify the model parameters. And there is some approach to locate and edit the weights where a certain fact is located. But as you can see, deep neural network in general is a black box. So this would result a lot to the methods which are used to explain these large language model. So for example, in the Rome paper, which you can take a closer look later, they try to locate the edits related layer by destroying and subsequently restoring the activation. As in they would try to destroy some activation and then see how much it changed in the model output to locate where exactly one fact is located in the large language model. And then they would look into the methods on how to restore this activation in order to output actually what we want. Another way is to do meta-learning methods, where we train an external hyper network to predict the weight update of the original model. For all of these methods, we need access to the large language model itself, which again is not always available for models such as ChatGPT. So people have also been looking into the approaches which preserve the model parameters, where we use additional model plug-in into the original model in order to just change the output of that model based on our preferences. Another way to mitigate hallucination coming from knowledge boundary is to do retrieval augmentation. So here we would do everything in two steps. So when a question is arrived, we would first retrieve relevant documents from external sources. And then during generation, we would make the large language model output conditioning only on the input text and the retrieved documents. And in this way, we would somehow try to shift the focus of the large language model on the document that was retrieved by the previous step, rather than making the model just rely on its own pre-trained knowledge. So somehow it would increase the assurance that the model would focus on the right knowledge. And the next approach is to mitigate the knowledge recall failure. And one way is to do chain of thought prompting. So this is quite commonly used recently, and it's also quite simple in the sense that you can just ask the large language model to first output the reasoning and then output the final result of whatever the question was. So I think all of these methods are, and all of these processes of hallucination are somehow connected because if we do chain of thought prompting, somehow we are forcing the model to output the reasoning first, and then in the final step, when it's output the actual answer for the question, in those next word prediction, it would be the model, the large language model would be conditioned on the source input and also on its own reasoning because of the autoregressive decoding process. Another way, simpler, is just to directly supplementing the questions with relevant information. So I guess in some sense, it's also quite similar to what we have seen before with the retrieval augmented method. But then the question here is quite difficult because which information is relevant and then which information is useful. The next one is to mitigate pre-training related hallucination. So here we will see a factuality enhanced training method. So during training of the large language model, we would usually have to truncate the documents, the text document, into smaller chunks because otherwise we cannot fit everything into the GPUs at once because there's a limitation in computational resources. So by this truncation process, somehow the information from the document would be fragmented, and then there can be incorrect entity association because when we split the document, we no longer know, for example, what is it referred to or what is her referred to. So this can also be a problematic issue. And then one way of fixing this problem is where people just append a topic prefix to each sentence in factual documents. And then they would transform each document into a standalone fact with the hope that the model would be able to see the relevant based on this topic prefix. And the next aspect is how to mitigate inference-related hallucination. We can do confidence decoding, which is during the decoding process, we try to incorporate a confidence score. And then whenever the confidence score is low, we try to emphasize the source more, as in we try to make the model not to only look at the tokens that is close to it, but also look at the inputs that is further to it, which is the source sentence. Another way is to use automatic faithfulness metrics to rank candidates generated by beam search. So usually when we do beam search, we will just try to look for the output sequence that have the highest probability confidence. But if we try to incorporate faithfulness metrics into the generation process, it would be a way to just directly optimize for this faithfulness metrics. So that could also be a way of handling it. But then again, we should also be careful because we might be overfitting into some metrics rather than to actually improve the quality of the generation. Okay, so that was all on hallucination for large language model. Does anyone have any comments or discussion point? Okay, so now we'll go into hallucination in machine translation. So hallucination in machine translation is defined as when the translation is irrelevant to the source sentence. So personally, I think this is easier to identify than hallucination in large language model, because in order to see whether an output is hallucinated or not, you just have to compare it with the source sentence itself. While for large language model, in order to know whether it's hallucinated or not, you have to have enough domain knowledge and to be able to verify whether the output is conflicting to some facts, and looking for the facts and the knowledge is quite exhaustive. And unlike a large language model, hallucination in machine translation doesn't happen very often. This is why one survey paper for hallucination in machine translation is like looking for a needle in a haystack. So, but then it can severely harm the user trust, because if you can imagine that some machine translation model, most of the time to output very good translation, but then once in a while, very rarely output something that is completely irrelevant to the source sentence, then it would be very difficult for the user to know when to trust the model or not. So somehow this is also problematic, but in a different direction than hallucination in LLMs. So now we will also go into taxonomy of hallucination for NT. The first type is oscillatory hallucination, is when there is erroneous repetitions of words and phrase. I guess this happens a lot when you have a not very strong machine translation model, which tends to be stuck in some decoding loop and then fail to output the end of token, end of sentence token, and then it just keep repeating some piece of text. And here is one example where the reference translation is the case where based on something is referred to as aporia. And the hallucination one is aporia is the name of aporia, which is the name of aporia, which doesn't make sense. And it seems like the model here just stuck in outputting the same thing over and over again. However, this type of hallucination is somehow kind of safer because as soon as we look at this hallucinated output, we know that something is wrong with it, and we know that most likely we shouldn't trust this output. However, a more dangerous type of hallucination is largely fluent hallucination, which are fluent. However, they are completely unrelated to the content of the source sequence. So here you can see two examples. Tickets from, well, again, the first one is reference translation, and the second column is the hallucinated translation. So tickets for buses and the subway is too expensive, especially in Stockholm. And then the translation by the model is the hotel is located in the center of Stockholm, close to the train station. So as you can see, it is, well, I guess it is related to the source sentence in the sense that it both mentions Stockholm, but however, content-wise, it's not the same. And the second example is head up to the rooms, open up the windows, and savor the view deeply more. And then the output is the staff were very friendly and helpful. So in this case, it's not even relevant that much at all compared to the reference translation. However, both of these sentences sounds really fluent, and if you don't speak both language, if you don't have any knowledge on the source sentence, it's going to be quite difficult for you to tell that these translations are bad just by looking at the sentence itself. So people pay more attention on hallucination detection for NT. So the general approach for hallucination detection for NT is that we would first filter out the translation with low quality defined by some matrix, and then we would combine it with some heuristic. So for deciding the low quality examples, we can use some reference-based metric like chart2 or Comet, or we can use reference-free metrics like Comet QE. So well, chart2 is some traditional surface level metrics, whereas Comet and Comet QEs are narrow-based metrics. But in any case, it would give some score indicating how good the translation is on the sentence level, and then we would be able to filtering out the one with the low quality. But however, low quality translation doesn't always mean that it is hallucinated sample. Well, because by definition, the hallucinated samples should be the ones that is completely detached from the source input. So we will have to combine it with some heuristic. So here are a few heuristic. That's some survey paper list. And the first one is top n-gram count, where they count the number of repeated n-gram in the translation, and then they subtract it by the repeated n-gram in the source sentence. And if this is larger than the threshold, then most likely that the model is hallucinating and being stuck in a decoding loop. So that's the first heuristic. The next one is repeated targets. This happens when people input multiple different unique source sentences into the model, but still getting the exact same sentence out. Then most likely the model have just seen this target sentence so much in the training data that it just memorizes it and keep outputting it. Doesn't matter which sentence was input to it. Another way is to look at the retention mechanism. some people have found that when the most attention mass is concentrated on the short end of sentence tokens, then it's more likely that the model is actually not paying attention to the correct part of the sentence, and is most likely to hallucinate. And the last heuristic is to use uncertainty-based method. Again, we can look at the sequence log probability output by the model itself, or we can look at the dissimilarity of different hypotheses output by the model when we do Monte Carlo sampling. So for mitigation for MT, somehow it's a bit more narrow compared to mitigating hallucination in LLMs, because as I mentioned before, it doesn't happen that often for MT. So here for mitigating hallucination scenario, we can just simply override hallucination at text time. So the more important question is how are we going to detect them? But anyway. So one approach that was proposed by the survey paper is to generate several MC dropout hypothesis and then just choose the one with the highest score. And this score can be some, again, metrics like comment or commit QE. And then surprisingly, the paper find that just by doing this simple approach, most hallucinations and errors become correct, which means that in most cases, the model is actually not stuck in a hallucinatory mode, but it's more like a bad luck case when it just outputs something irrelevant. And if we look at the different examples generated by the model, there can be some good translation somewhere in there. So that would be all for mitigation. Okay, so these are the paper resources which I use for this lecture, and you can take a deeper look into, but that is all for the content. So if you have any question, you can ask it now, or otherwise you can end the lecture early. Okay, if not, then thank you for your attention.